Okay, good afternoon. This is Professor David J. De Los Reyes. Good afternoon, Los Angeles. My topic this afternoon will be lesson number 85 on the topic integral calculus. That is on my channel. The topic is integral calculus. Subtopic is length of arcs. The main topic for this afternoon is the derivation of the circumference of a circle. Okay, let's proceed, guys, so we don't waste time. I will try to read the problem. Derive by integration the circumference of a circle of radius r. This will now be an application of integral calculus. We are now through with the plane areas. We are now through with the volume. So the third climax topic is actually the length of arcs. In real life, this will be an application of the computation of length of transmission lines. So this is actually especially needed for electrical engineers. Okay, let's try to bring out the figure. If we try to solve the problem here, we will bring out the Cartesian coordinate system. So this should be the y-axis. This is the x-axis. And since the figure is actually circle, we drew a circle here with the radius r. So this is the configuration of the circle on the Cartesian coordinate system. Okay, let's proceed. If we try to compute for the total length of the circumference, we will use symmetry here. We will just compute 1/4 portion, then times 4. So meaning, dx, differential x, should move from 0 to r. Okay, this dx here, then times 4. So actually on the right hand side, we got a times 4 over here. Okay. Let's try to bring out the general equation that was derived yesterday. Differential length of r equal to the square root of 1 plus dy over dx quantity square multiplied by dx. We call this equation number 1. Okay. To integrate differential length of arc, we will try to compute dy over dx as a function of your x. Because the differential on the right hand side is dx, it is a must that we will compute for dy dx as a function of your x. And we will get that relation from the equation of the circle. The equation of the circle with center at 0, 0 is actually x squared plus y squared equal to r squared. Okay? So we will get the relation of dy dx from this equation here. It is from analytic geometry. X squared plus y squared equal to r squared is actually an equation of a circle with center at 0, 0 and the radius of r. Okay, let's proceed. X squared plus y squared is equal to r squared. Solving for y squared, this should be r squared minus x squared. Taking the square root of both sides, these two here cancel with this. So on the left hand side, what will remain will be y. Right hand side will be r squared minus x squared. Okay. Let's try to compute for dy dx. The derivative with respect to x of y, it is just simply dy dx equal to, the right hand side falls under the power formula. And if we try to take the derivative of this, it should be nu raised to n minus 1 times du. The value of n is actually 1/2, so this is 1/2. The value of u is r squared minus x squared. 1/2 minus 1 is minus 1/2. Times the differential of the terms inside, this will be 0 minus 2x. And if we try to simplify this one, dy dx will be minus x all over the square root of r squared minus x squared. But if we try to go back to equation number 1, what we need is actually dy dx quantity square. So again, we will square both sides. Okay. So dy over dx quantity square is actually dy dx quantity square equal to the right hand side, just square the right hand side. Minus x quantity square will be positive x square. The square of the square root of r square minus x square. The radical sign will vanish. So dy dx quantity square in terms of your x is actually x square over the r square minus x square. If we get this value now, we put it back to equation number 1, differential length of r equal to, we are just following this, equal to the square root of 1 plus the square of the first derivative, which is x square over r square minus x square. Because we solve it separately to be systematic, times dx. And if we try to simplify this one, what will come out for the differential length of r? As a simplification, this will be r square over r square minus x square, the square root. Okay? And luckily, the numerator is actually a perfect square. This is times dx. So it will be r dx all over r square minus x square, the square root. Okay? I just go back here. Okay? Therefore, differential length of arc equal to, like what I said a while ago, to take the two circumference, just take 1/4, then times 4. So this is 4. The integral from dx should move from 0 to r. So the lower limit is 0, the upper limit is r. It will be r dx all over the square root of r square minus x square. So to compute for the circumference, okay guys, bring out your knowledge of integration. And if we try to inspect the resulting equation, it falls under trigonometric substitution. We are done with the different integrations, okay? So using trigonometric substitution, because for the meantime, the right-hand side does not fall under the power formula. We will let x square equal to r square sine square of theta. Taking the square root of both sides, they are all perfect squares, so this will be x equal to r sine of theta. Taking the differential of x will be dx, this will be r cosine of theta, differential theta. We need this value here to place it back, so we could evaluate the integral. And if we try to compute for the square root of r square minus x square separately to be systematic, this will be the square root of r square minus x square. From our substitution, it will be r square sine square of theta. Factoring out r square, this will be r square times the quantity 1 minus sine square of theta. But 1 minus sine square of theta is actually cosine square of theta. Perfect square, take the square root. What will come out will be r cosine of theta. If we try to evaluate the integral of the right-hand side separately to be systematic, the integral of r dx over the square root of r square minus x square equal to the integral of r times dx. Dx is r cosine of theta, differential theta, all over the equivalent of this, which is r cosine of theta. This is r cosine of theta. And luckily, r cosine of theta cancel with this. So what will remain on the right hand side after the trigonometric substitution, it will just be simply r, the integral of differential theta. And this is r times theta. Okay? We will express theta in terms of x, so we will go back with the substitution x equal to r sine of theta. Solving for r sine of theta, or sine of theta rather, this should be x over r. Taking the arc sine of both sides, the arc sine of theta is just theta, and the arc sine of x over r is just the arc sine of x over r. So the equivalent of theta in terms of x is actually arc sine of x over r. So if we try to go back to the original equation, we are now solving for the circumference of the circle. The circumference of the circle now equal to, we are following this, 4 times the integral of this, and in which it was a very low solution, it is actually r, okay, arc sine of x over r with the limit from 0 to r. So this should be 4r. If we try to place the upper limit, this will be arc sine of r over r minus the arc sine of the lower limit, which is 0 over r. R over r is actually 1. Okay? And the arc sine of 1 is actually pi over 2. It is 90 degrees. And the arc sine of 0 over r is actually 0. And the arc sine of 0 is actually 0. So actually the lower limit is, this is minus 0. Okay? But minus 0 has no effect on the final answer. So what will come out will be, okay, this should be 4r times arc sine of 1 is actually pi over 2. And this 2 here cancel with this. So what will remain for the circumference of the circle will be 2 pi r. This is 2 pi r units. So actually the formula we are using under lower mathematics under solid mensuration, in which the circumference of the circle is 2 pi r equal to pi d, actually emanates from integral calculus. That is the importance of integral calculus. All the formulas we are using under lower mathematics was derived from integral calculus. Okay, so the final answer, circumference will be 2 pi r or equal to pi d units. Good afternoon, Los Angeles.